For any function y equal to f of x of one variable, its derivative is defined by this general formula. And we interpret this as the rate of change of y with respect to x over the infinitesimal change in y, which is dy, resulting from a corresponding change in x, which is dx. For example, having a function f of x equal to x cubed, its derivative or rate of change with respect to x is 3x squared. But what if we have more than one variable, like the function is seen here, or this one, or even a function with 3 variables like this? We need to find similar mechanisms, like we did in here, to find the rate of change of these functions. And that's where partial derivative comes. The idea in here is to find the derivative of these functions with respect to only one variable, while holding the other variable as constant. Meaning, since we have a function with multiple variables, we try to find the rate of change of the function with respect to only one variable. And in doing so, we consider the other variable has some constant and derive them. And we do that for all other variables to find the rate of change of the function with respect to them. Having a function with multiple variables, here are some of the notation commonly used when we partially differentiate them. We use the curly d symbol you see over here instead of the usual d to emphasize that there are other variables during the differential process. For example, let's find the partial derivative of this function. First, with respect to x, considering y as a constant. So, the derivative of x squared becomes 2x, and since we consider y as a constant, the derivative of y squared with respect to x equals to 0. So we have 2x. Next, with respect to y, while holding x as a constant. So, since x is a constant, the derivative of x squared with respect to y would be 0. And the derivative of y squared with respect to y is 2y. So we have 2y. Doing another example, let's find the partial derivative for this function. So, to find the partial derivative, first, let's derive it with respect to x. So to do that, we use product rule. Now, using the product rule of derivatives, let's say f is x to the power of 4 and g is sine of xy cubed. So the expression becomes this. And when we solve this, we get our answer. Same with the partial derivative with respect to y, in which case we differentiate with y and get this answer. So far, we have been taking the partial derivatives only once, but we know that for a function of one variable, we can get first order, second order, third order, and so on higher order derivatives by successively differentiating them again and again. And we can do the same to find higher order partial derivatives. Given a function of two variables, z equals to f of x and y, its partial derivatives with respect to x and y may be a function of two variables, and they themselves may have a partial derivatives with respect to both variables. And those would be the second order partial derivatives. And in the case of a function with two variables like we have here, we get 4 second order partial derivatives. And those are also divided into two pure and mixed second order partial derivatives. Now, let's find the 4 second order partial derivatives for this function. First, we partially differentiate the function to get the first order partial derivatives with respect to x and y. And now, since the partial derivatives are a function of two variables, we differentiate them again with respect to both variables to get second orders. Starting from the left side, when we partially differentiate with respect to x and y, you get this. And for the right side too, we differentiate it with both variables and we get this. And so, we have all 4 second order partial derivatives. And it's the same for third and so on orders. We just successfully differentiate the partial derivatives themselves with the variable we have. Here are an example of third and fourth order partial derivatives. To give an example, let's find this third order partial derivative for this function. Expressing the subscript notation with the symbolic one, we get this. Both represent the same thing, but they have opposite conventions for the order of differentiation. In the subscript notation, the derivatives are taken from left to right. And in the symbolic one, they are taken from right to left. So, in this case, they both represent, first, differentiating the function with respect to x, and with y 2 times. So, when we differentiate with respect to x, we get this. Next, when we differentiate with respect to y, we did this. And finally, when we differentiate again with y, we did this. And this is our answer. Thank you for watching, and if you find this video helpful, subscribe for more.